Welcome back to Introduction to Higher Mathematics. In our last lecture, we went in a different direction with our discussion of the real numbers, when we talked about sequences. We briefly defined notation for sequences, using angular brackets to distinguish them from sets and tuples. Then we went right into properties of various sequences. We saw that sequences can be monotonic. That is, they could be increasing or decreasing. If we don't allow successive terms to be equal, they can be strictly monotonic. We also saw that sequences can be bounded, from above, below, or both, or perhaps unbounded. We found that some sequences converge to a single limit, meaning as n goes to infinity, the terms of the sequence approach some number to any degree of precision. We introduced Cauchy sequences, sequences where the terms get closer to each other. And we noticed that in the real numbers, every Cauchy sequence is convergent. This is what we mean when we say that the real numbers are complete. Finally, we saw that many of the same concepts we discussed applied to functions, especially when it comes to limits, which are the foundation upon which the field of calculus is built. What we're about to get into now will begin to reveal some of the underlying structure that supports all of mathematics. Hopefully, after these next few lectures, you'll begin to see math from a wholly different and enlightened point of view, because we're going to build some relationships that connect math in a truly beautiful way. What we're about to embark on is a study of what are called groups. The tale of group theory begins in 19th century Europe. Prior to that point, the quadratic formula had long been known since the time of Brahmagupta in 7th century India, and explicit solutions for the cubic and quartic equations had been published in Cardano's Ars Magna in 1545. Now the race was on to find the solution to the elusive quintic equation, a polynomial of degree 5. Many mathematicians had tried to find a solution, but without success. Enter two young talented mathematicians, a Norwegian named Niels Henrik Abel and a Frenchman named Évariste Galois. Each of these young men independently proved instead that the general quintic is not in fact possible to solve using only basic addition, subtraction, multiplication, division, and extraction of roots. Instead, more complicated mathematical tools must be employed to find analytic solutions. Abel published the result first in 1824. Building upon results by Italian mathematician Paolo Ruffini, so the theorem is today known as the Abel-Ruffini theorem. However, it was Galois' work that was truly stunning and that really elucidates the situation. He built his solution on what he named groups, which were soon to become a powerful unifying concept in math, describing things in terms of symmetry. Unfortunately, Galois' proof that the general quintic and higher polynomials can't be solved using simple mathematical operations was published posthumously. Galois was a passionate young man and a political radical, so he got himself into some questionable situations. He ended up being challenged to a duel, and he spent the night before the duel feverishly writing down his entire theory of groups as a sort of mathematical testament. The next morning, he was shot in the stomach and died the day after. He was 20 years old. By the way, Abel also died tragically young. He spent the latter part of his life quite poor, trying to get a teaching position in Berlin. A letter came finally saying that he had been appointed as a professor at a university, but that letter came too late, 2 days after Abel had died at the age of 27. How strange are the workings of the world in which two pioneers of symmetry would similarly both die so young. So let's get started with groups. A group is an algebraic structure that consists of a set and a single binary operation defined on members of that set. We usually represent it as an ordered pair. For right now, we'll use G for our set and a star for our operation. Sometimes you'll also see the group referred to just by the set if we already know what the operation is. For such a structure to qualify as a group, it must have 4 basic properties. First, we have the closure property. That is, the set must be closed under that operation, meaning that if we combine 2 elements of the set using our binary operation, the result must still be in that set. So if A and B are in G, then A star B must also be in G. Second, the operation must be associative, meaning that grouping elements together differently when combining 3 or more should not change the outcome. So, A star B star C must be the same whether we do A star B first or B star C first. Third, there must be an identity element, which is an element that will have no effect on any other element under the operation. So if our identity is called E, then A star E should be A, and E star A should be A, no matter what A is. Finally, every element must have an inverse, which is another element that when combined with the original will return the identity. So, if we represent the inverse of A as A to the negative 1 power, read as A inverse, then A star A inverse should be E, the identity, and A inverse star A should be the identity as well. We call these 4 properties the group axioms. By the way, the identity element and inverse elements are unique. See if you can prove this. Let's look at an example of a group, the group Z+, which is the group of integers under addition. How can we tell if this is in fact a group? Let's check all 4 axioms. If we add 2 integers, we'll definitely get an integer back, so the closure property is satisfied. Addition of integers is in fact associative, as you learned in grade school, so the associativity property is also satisfied. Now what would the identity be? It would have to be 0, as adding 0 to a number, or a number to 0, gives that same number back. So the identity property is satisfied. Finally, what's the additive inverse of an integer? Its negative counterpart. Any number plus the opposite sign of that number equals 0, which, as we just saw, is our identity. So the inverse property is satisfied, and our structure is in fact a group. Let's try another one. Will the integers form a group under multiplication? Again, let's check the axioms. If we multiply 2 integers, we'll always get an integer back. So the integers are closed under multiplication. Multiplication of integers is also associative. Now, is there an integer that will not affect any other number when multiplied by it? Well, it would have to be 1. Any integer times 1, or 1 times any integer, is that integer. But what about the multiplicative inverse? Consider 2. Is there an integer I can multiply 2 by to get 1? Unfortunately, no, there isn't. The equation 2x equals 1 has no solution in the integers. So the integers do not form a group under multiplication. But is there a set that would form a group under multiplication? When you first saw the equation 2x equals 1, you probably thought, well, x would have to be 1/2. But what is 1/2? It's a rational number. So do the rational numbers form a group under multiplication? We can easily verify that the closure and associative properties hold, and the identity is still 1. But does every rational number have a multiplicative inverse? Almost. Usually, if A is a rational number, then A inverse would just be its reciprocal 1 over A. There's one single exception, though. 0. 0 has no multiplicative inverse, because there's no solution to the equation 0x equals 1. Any number times 0 is 0. But if we exclude 0 from the set of rational numbers, then we have nothing to worry about. So the set of non-zero rational numbers does form a group under multiplication. Now, you may have noticed that there's one familiar and important property that the integers and rational numbers have that we didn't include as part of the definition of a group: commutativity. Commutativity is not part of the definition of a group. But must a group operation be commutative anyway? Perhaps can it be derived from the other 4 properties? To answer this question, let's look at another group, what we call the general linear group. The group GLN is called the general linear group of degree n, and the group GLN of R represents the group formed by n matrices of real numbers with non-zero determinants under matrix multiplication. We can also let R be replaced by the complex numbers if we want, or any other field, which we'll learn about quite soon. Let's check the group axioms for GL2 of R. 2 by 2 real matrices are closed under multiplication, as multiplying them yields another 2 by 2 real matrix. Matrix multiplication in general is associative, so it's certainly true for 2 by 2 matrices. There's an identity matrix that acts on 2 by 2 matrices, the matrix 1, 0, 0, 1. As for multiplicative inverses, since we restricted ourselves to only matrices that don't have 0 as the determinant, we've guaranteed that all our elements will have multiplicative inverses. So, as we said before, GL2 of R is a group. But there's something important to notice. Matrix multiplication is not commutative. Suppose we have two matrices, A equals 1, 2, 3, 4, and B equals 5, 6, 7, 8. Then A times B equals 19, 22, 43, 50. But B times A equals 23, 34, 31, 46. So commutativity is not necessarily a property of any group. If the group operation is commutative, then we call it an abelian group, named after none other than Niels Henrik Abel. So the integers under addition and the non-zero rationals under multiplication form abelian groups, but the general linear group is what we would call a non-abelian group. So far, we've seen three groups that have an infinite number of elements in their sets, which we would call infinite groups. However, we can have finite groups as well, in which the underlying set has a finite number of elements. In fact, we were introduced to an example, the integers mod m. Recall, for example, the addition table for Z5. We can see just by looking at the table that the closure property holds. All the entries in the table are elements of Z5. We can also see at a glance that 0 is the identity, and that every element has an inverse. That is, something that we can add to it to get 0. Associativity is a good bit harder to check, because we would technically have to check every single sequence of three numbers to verify it, though generally we don't have to check anything involving the identity. It turns out, though, that residue systems inherit associativity from the integers that they're derived from. We call a table that displays the results of all possible operations on members of a finite group a Cayley table, named after British mathematician Arthur Cayley, who further developed Galois' work on group theory, giving us the particular group axioms we use today. When we make a Cayley table, we get the first element from the row and the second element from the column. So to do 3 plus 4, we find the row corresponding to 3 and the column corresponding to 4 to find the sum. On the other hand, to do 4 plus 3, we need to use the row corresponding to 4 and the column corresponding to 3. In this case, though, since addition in Zm in general is commutative, the group's abelian, so both will give us the same result. In fact, we can tell the group is abelian just by looking at it. It's mirrored across its main diagonal. So let's use Cayley tables to create a group with three elements. Let's say that the elements of our set are A, B, and an identity E. Again, we'll make the operation be a star, since we don't really know what sort of operation it really is. So, setting up the Cayley table, we've got E, A, and B in the rows and the columns. First, we know by the identity property that A star E and E star A are A, B star E and E star B are B, and of course E star E is E. That leaves 4 spaces unaccounted for. Now, what should A star B equal? It can't be A, because that would mean that B is the identity rather than E. Remember, we can have only one identity element in a group. It also can't be B, because that would mean that A is the identity. So our only possibility is that A star B has to be E. For the same reason, we know that B star A also has to be E. So A and B are each other's inverses. With that out of the way, A star A can't be A because A isn't the identity. And A star A can't be E because that would imply that A is its own inverse, and we just showed that A's inverse is actually B. So our only option is that A star A equals B. Similarly, B star B equals A. And there you have it. There's only one possible finite group with 3 elements. What's more, If we replace a few symbols, something really interesting happens. Replace E with 0, A with 1, and B with 2. Well, look at that. That's the addition table for Z3. Wonder why that is. Keep that in mind for later. I won't spoil the surprise just yet. Now, let's extend the concept of a subset from set theory and talk about the concept of a subgroup. Suppose we have a group G star, and let H be a non-empty subset of G. If H also forms a group under that same star operation, then we can say that H star is a subgroup of G. As an example, suppose our group is the integers under addition, and let our subset be the even numbers, which we'll write as 2z, since every even number is 2 times some element of z. We know that adding 2 even integers always yields an even integer. Since addition is associative for all integers, it's certainly true for even integers in particular. The additive identity 0 is an even number, and if a is an even number, then negative a will also be an even number. So, the even integers form a subgroup of the integers under the same operation of addition. It turns out that all you need to do to check if a subset H of a group G forms a subgroup is 2 things. First, H must be closed under the operation. And second, if X is in H, then X inverse must be in H as well. If these 2 criteria are met, H is a subgroup. Let's use these facts to see if the odd integers are also a subgroup of the integers under addition. If a is odd, then its inverse negative a will also be odd. However, the odd integers are not closed under addition. An odd plus an odd will in fact be even. What's more, if G is a finite group and H is a non-empty subset of G, then all we need to do is check the first criterion, that H is closed under the operation. For example, consider the group Z6 under addition. What happens if we consider just the even numbers 0, 2, and 4? Well, let's look at just those rows and columns of the Cayley table. Notice that our subset is in fact closed under addition mod 6. So we can say that the set 0, 2, 4 with mod 6 addition is a subgroup of Z6. This wouldn't be the case if we were using the same set as a subset of, say, Z5. The table shows that our subset is not closed under addition mod 3. So 0, 2, 4 is not a subgroup of Z5 under addition. Every group has 2 particular subgroups. First of all, the group consisting of a set with only an identity element is called the trivial group. Since the trivial group is always a subgroup of any group, it is often called the trivial subgroup. Second of all, any group is, of course, considered a subgroup of itself. As you might expect, a subgroup formed from a proper subset of our original set is called a proper subgroup. So 2z is a proper subgroup of z. To continue working with subgroups, first we need to talk about exponentiation notation. If G star is a group and A is an element of G, then A star A can be written as A squared, even if our group operation happens to be addition, as long as the context is clear in that we're only working with one operation. Then, we can also define other powers of A by successively applying A to itself with our given operation. And of course, A to the 1 is just A. We can also define 2 other special kinds of powers. First of all, we can define A to the 0 as the identity element. Second of all, we can see why the negative 1 power actually makes sense for the idea of an inverse. Using the conventional exponent rules you know from regular algebra, A to the 1 times A to the negative 1 equals A to the 0, which is the identity. From this, we can further define negative powers of A as just positive powers of A inverse. Now, suppose we take an element A of a group G, and we look at all possible powers of that element. In other words, we find the set of all A to the n such that A is in G and n is an integer. When we do this, we will be guaranteed to get a subgroup of G. We call this the subgroup of G generated by A, and we call A the generator of the subgroup. We write this subgroup as an A within angle brackets like this. So consider Z6 from earlier. Remember that exponentiation in an additive group is repeated addition, which is actually just multiplication, but we'll get to that later. What is the subgroup generated by the element 2? Well, 2 to the 1 is, of course, 2 itself, and 2 to the 2 is 2 plus 2, which is 4. Remember, 2 to the 2 just means do the operation 2 itself twice. If we continue, we find 2 to the 3 is 2 plus 2 plus 2, which in Z6 is 0. We've managed to wrap back around the identity. Finally, if we do 2 to the 4, then that's 2 plus 2 plus 2 plus 2, which is back where we started at 2. So the subgroup generated by 2 is the set 0, 2, 4, under addition mod 6. What's more, we say that the order of an element is the number of elements in the subgroup it generates. So since the subgroup generated by 2 has 3 elements, we say that in Z6, the order of the element 2 is 3, which we write using absolute value bars. We can also generate a subgroup using a set of elements. If we start with 2 elements, for example, A and B, then the subgroup generated by A and B is the set of all elements that can be expressed as some combination of A's and B's in some order. So, what is the subgroup of Z6 generated by the set 2, 3? Well, using 2 as a generator, we get 0, 2, 4, and using 3 as a generator, we get 0, 3. So far we've got 0, 2, 3, and 4. But dropping the exponentiation notation and reverting back to just simple addition, we can combine these elements to get still others. 3 plus 2 equals 5, and 5 plus 2 equals 1. So the subgroup generated by the set 2, 3 is actually the entirety of Z6. Now for a very important question. What is the subgroup generated by 1? Well, 1 to the 1 is 1, 1 to the 2 is 1 plus 1, which is 2, 1 to the 3 is 1 plus 1 plus 1, which is 3, the list goes on, until we've managed to generate the entire group. So the subgroup generated by 1 is actually the original group, Z6, and we can actually say that 1 is a generator of Z6 itself. When we can generate an entire group by just a single element, we call that group a cyclic group. We call it cyclic because we can kind of imagine the elements drawn in a circle, such that successive powers are arranged one right after the other. But does Z6 have any other generators? It turns out there is one more, 5. Let's take a look. 5 plus 5 is 4, 4 plus 5 is 3, 3 plus 5 is 2, 2 plus 5 is 1, and 1 plus 5 is 0. Why is 5 another generator of Z6? Well, look at the relationship between 1 and 5. They're actually inverses of each other. It turns out that the order of an element is always the same as the order of its inverse. Again, see if you can prove this. It may come as no surprise that Zm under addition is a cyclic group for any natural number m. But even infinite groups can be cyclic. A great example is the integers under addition, which can be generated by 1 or negative 1. So, if all these groups are cyclic, what might a non-cyclic group look like? Let's consider a special group called the Klein 4 group, notated as V, which stands for the German word Vierergruppe. The Klein 4 group has 4 elements, which we'll denote as E for the identity, of course, A, B, and C. Now the operations are defined like this. Besides the normal identity relations, A squared, B squared, and C squared are all E. And out of A, B, and C, any one of the 3 times another is the third. So you can see that the Klein 4 group is actually abelian. But since every element is of order 2, it cannot be generated by a single element, so it is not cyclic. In fact, the Klein 4 group is actually the smallest non-cyclic group. Let's look at one more class of groups that's incredibly important in group theory, the permutation groups. Given some sequence of objects, a permutation of those objects is a rearrangement of the objects, putting them in some order. In terms of functions, a permutation can be thought of as a bijection from a set to itself. You may have already learned that the number of possible permutations of n objects is equal to n factorial. That is, n times n minus 1 times n minus 2, and so on all the way down to 1. So for instance, if we have 3 different colored balls, perhaps red, green, and blue, then there are 3 factorial, or 6, different arrangements of those balls. When we're doing group theory, though, we're not so much concerned with the number of different arrangements as much as we are with the processes by which we obtain these arrangements. So let's consider each of the permutations of the 3 colored balls. What would we need to do to get each one? Let's assume in each of these cases the balls start off in the order red, green, blue. First of all, we could just leave the 3 balls alone, so they stay the same color, red, green, blue. Any idea what we would call this permutation? It's called the identity permutation, since it leaves our items untouched. So we'll call that particular transformation E. Next, we could hold the first element constant and transpose the last 2 elements, giving us red, blue, green. Let's call that transformation tau 1, since tau is the Greek letter T, which in this case will stand for transposition. Similarly, we could hold the second one constant and transpose the outside 2 elements, giving us blue, green, red, which we would call tau 2. Or we could hold the last one constant and transpose the first 2 elements, giving us green, red, blue, which we'll call tau 3. That's 4 permutations so far. We still need 2 more. Well, we could move the first ball to the back, giving us green, blue, red. Basically, cycle the elements around. Let's call that one sigma 1, since sigma is the Greek letter S, which is the first sound in the word cycle. Or we could move the first 2 balls to the back, giving us blue, red, green. And we can call that one sigma 2. So there we have it, 6 elements, each of which corresponds with one of our permutations, leaving no permutations unaccounted for. Now, suppose we want to see what happens if we successively perform multiple permutations on an ordered triple of objects. Since a bijection is a kind of function, we can treat permutations as if they were functions, in which case successive permutations are like compositions of functions. In addition, this means that if we perform the composite permutation P1 of P2 on a tuple, we actually perform P2 first, then P1. Remember that composition of functions are performed in the opposite order that they're written. So with this in mind, let's make a Cayley table. I won't do the entire thing since this is a 6x6 table. Just some examples to show you how we might approach this. First of all, since E is the identity permutation, any permutation composed with E in any way is just that permutation. So the first row and first column are easy. Now consider the cycles next, sigma 1 and sigma 2. If I move one element to the back and then move another element to the back, it's the same as if I'd moved 2 to the back to begin with. So sigma 1 of sigma 1 is sigma 2. On the other hand, doing sigma 1 first and then sigma 2 would actually bring us back to our beginning position as if we'd done nothing at all. So sigma 2 of sigma 1 is the identity E. Remember that sigma 2 comes first. Remember that in our notation, sigma 2 is first and sigma 1 is second. So sigma 2 is the row element and sigma 1 is the column element. However, these permutations are applied in the opposite order. Sigma 1 actually is applied first, and then sigma 2 is applied second. What about the transpositions of 2 elements? Well, if we switch 2 elements, and then switch those same elements back, it's as if we never touched them at all. So any of our transpositions composed with itself is the identity E. What if we do 2 different transpositions in a row? Say we do tau 1 first, then tau 2. So we swap the last 2 elements, then swap the outside elements. Well, it looks just as if we'd moved red to the back in the first place, doesn't it? So the composition of two transpositions is a cycle. In this case, tau 2 of tau 1 equals sigma 1. Now that you have an idea of how the various compositions are calculated, take a look at the full Cayley table. From the looks of this Cayley table, we can see that our permutations are closed under composition, and every permutation has an inverse. You'll have to take my word on the associativity unless you really want to try every single possibility out. But, as it turns out, the set of all permutations on 3 elements forms a group under the operation of composition. Not only that, but it's non-abelian, as you can see by examining the table. And it's also non-cyclic, since the cycles are of order 3 and the transpositions are of order 2. No single element generates the entire group. Thus, this is our first, and actually smallest, example of a non-abelian, non-cyclic group. We call this group of permutations the symmetric group on 3 elements, which we abbreviate as S3. In general, the same applies to permutations on n elements, which will be the group Sn. The permutation groups are incredibly important, as not only are they the ones that Galois was originally studying that led to his conclusion about the general quintic equation, but in a way, every group in existence is related back to these permutation groups. That's it for this lecture. In the next lecture, we'll be using groups to build new structures called rings and fields. In doing so, we'll be seeing more and more of why our number system works the way it does. See you next time.